Completely fair scheduler. Completely fair scheduler is a process scheduler that was merged into the 2.6.23 release of the Linux kernel and is the default scheduler of the tasks of the Sched normal class. CFS does not use all data structure for the run queues, but it uses time-ordered red block tree to build a timeline of future task execution. And this is the example of a red block tree, with tasks represented by Sched entity objects stored in the time-ordered red block tree. Tasks with the greatest need for the processors or lowest virtual runtime are stored toward the left side of the tree, and tasks with the least need of the processor or the highest virtual runtimes are stored toward the right side of the tree. The scheduler then, to be fair, picks the leftmost node of the red block tree to schedule next to maintain fairness. The task accounts for its time with the CPU by adding its execution time to the virtual runtime and is then inserted back into the tree if runnable. In this way, tasks on the left side of the tree are given time to execute, and the content of the tree migrates from the right to the left to maintain fairness. Therefore, each runnable task chases the other to maintain a balance of execution across the set of runnable tasks. CFS internals. All tasks within Linux are represented by a task structure called task struct. These structures, along with others associated with it, fully describe the task and includes the task's current states, its stack, process flags, priority or both static and dynamic, and much more. You can find this and many of the related structures in, but because that all tasks are runnable, you won't find any CFS related fields in the task struct. Instead, a new structure called Sched entity was created to track scheduling information. So this is the structure hierarchy for tasks and the red block tree. The relationship of the various structures are shown in figure 2. The root of the tree is referenced via RB root elements from the CFS RQ structures. Leaves in a red block tree contain no information, but internal nodes represent one or more tasks that are runnable. Each node in the red block tree is represented by an RB node, which contains nothing more than the child references and the color of the parent. CFS features. CFS supports symmetrical multiprocessing or SMP, in which any process, whether kernel or user, can execute on any processor, yet configurable scheduling domains can be used to group processors for load balancing or event segregation. Configurable scheduling groups are another CFS features. The particular worker that handles the request is irrelevant. It matters only that the request is handled in a timely manner, and so the four workers together provide a pool from which to draw a task handler as requests come in. CFS implementation. CFS requires efficient data structure to track task information and high-performance code to generate the schedules. Let's begin with the central term in scheduling, the run queue. This is a data structure that represents a timeline for scheduled tasks. Despite the name, the run queue needs to be implemented in the traditional way as a FIFO list. CFS breaks with tradition by using a time-ordered red block tree as run queue. Priorities and CFS. CFS doesn't use priorities directly, but instead uses them as a decay factor for the time a task is permitted to execute. Lower priority tasks have higher factors of decay, where higher priority tasks have lower factors of delay. This means that the time a task is permitted to execute this dissipates more quickly for a lower priority task than for a higher priority task, than an elegant solution to avoid maintaining run queues per priority. Scheduling class and domains. As introduced with CFS is the idea of scheduling classes, or recall from figure 2, Each task belongs to a scheduling class, which determines how a task will be scheduled. A scheduling class defines a common set of functions via sched class that define the behavior of the scheduler. For example, each scheduler provides a way to add a task to be scheduled, pull the next task to be run, yield to the scheduler, and so on. Each scheduler class is linked with one another in singly linked list, allowing the classes to be iterated, for example, for the purposes of enablement of disablement of on a given processor. This is the graphical view of scheduling. But recall the scheduling classes are part of the task structure itself. This simplifies operation on tasks regardless of their scheduling class. For example, the following functions preempts the currently running task with a new task, where cure defines the currently running task. RQ represents the red blocks tree of for CFS, and P is the next task to schedule. Then going further, if there's one constant with Linux, it's that change is inevitable. Today, the CFS is the 2.6 Linux scheduler, but tomorrow it could be another new scheduler or a suite of scheduler that can be statically or dynamically invoked. There also a certain amount of mystery in the process behind the CFS, RSDL, and the kernel inclusion. But thanks to both Colibas and Molinar's work, we have a new level of fairness in 2.6 task scheduling.